let's calculate the wavelength corresponding to an object of mass 1 kilograms moving with velocity 1 meter per second. So this is the block of mass 1 kg moving with 1 meter second velocity. We all got the formula P equals to h by lambda. So correspondingly we can calculate it. Lambda equals to h by p. So let's calculate the momentum and its corresponding wavelength. Let's see what the value of wavelength is corresponded to the mass of a particle 1 kg moving with velocity 1 meter per second. So lambda equals to h by mv, mass m equals to 1 kilograms, we put in SI, velocity is 1 meter per second also in SI units, and the Planck's constant is 6.6 into 10 to the power minus 34 also in SI. So dividing by 1, basically we are coming to the same value. So the wavelength corresponding to that 1 kg mass block is this. Now can we see the problem with this wavelength? Yes, the order. The order is 10 to the power minus 34. Usually the light we observe, the visible light, is in the order of wavelength 10 to the power minus 8, 10 to the power minus 10. This is the order of wavelengths of different kinds of waves you observe, and also larger than this. But this 10 to the power minus 34 is multiple times smaller. It's very infinitely small with respect to the things we observe in our daily life. So we can conclude from here that the matter waves, which are waves corresponding this kind of masses, are extremely small to observe, and that is why we cannot see the waves coming out of these pens or other things. Now if someone is thinking that if I increase the mass or the velocity, the matter waves might get larger and we can observe them. It's not, because mass and velocity both are inversely proportional to the wavelength. If I increase mass or if I increase the velocity, I will divide this quantity by a higher value, so I will get more lower values. So you can understand that we cannot find these wavelengths. Clear? Now let's see what can I plot in the graph to understand the characters. That lambda equals to h by p, and if the object or the particle is moving is at other velocity than c, we can represent the velocity by v. So p is momentum, that is mass into velocity, so p equals to mv. So one important characteristics that comes out from here is that if the object is at rest, that its velocity is 0, then v equals to 0, so lambda becomes something divided by 0, that becomes infinite. So we can understand that we can only get the waves, the matter waves, if the object is not at rest. The object must be in motion. That means velocity cannot be 0. The velocity must be greater than 0 to acquire any value for matter waves. And one more important thing is that if we plot their nature in graphs, it comes out like this. Here I have plotted momentum p with wavelength lambda. The graph is like this. Yeah, for 0 momentum and these higher cases, we can see it is a inversely proportional graph. When v lambda is smaller, the value of p is very high, and when lambda is larger, the value of p is very small. That is why, because of its relation of inversely proportional. And if I plot mass versus wavelength, we are also getting the same kind of relation, because lambda equals to h by p, that is h by mv. So mass and wavelength are also inversely proportional to each other. That is why we also get that similar kind of graphs. Now let's see what more we can get. If we are planning to calculate the kinetic energy from them directly, we know that kinetic energy, which is represented by k, is half mv square. Now we know wavelength lambda equals to h by mv. So what can I say? That let's put the value of kinetic energy in this equation, but we cannot directly put them. Say k kinetic energy is half mv square, so 2k into m is m square v square. So mv equals to root 2km, and that is P. Now you might be thinking that there should be a plus minus here. It's not, because it's momentum, we are only considering the positive value. So lambda equals to h by mv, that is h by p. It is also written as h by root 2mk, where k stands for kinetic energy. This is the relation between wavelength and kinetic energy. H by root 2mk. That's a very important equation. How? Let's say further that if the kinetic energy of electrons we are using, we all know their kinetic energy is represented by charge multiplied by their potential difference. The charge of an electron is E, and the potential difference considered as V. In that situation, what we get is h by root 2m. In place of k, we are putting the kinetic energy of the electron, that is EV, that is root 2m EV. This equation is very much important to calculate. Very important thing. So I hope this one is clear till now. So the equation of wavelength of electrons we got lambda equals to h by root 2m EV. Now most of these values are known to us except the V, the potential difference, which we will use to accelerate the electrons. We know the value of mass. Mass is 9.1 into 10 to the power minus 31 kg. The charge of the electron is 1.6 into 10 to the power minus 19 coulomb, and H is Planck's constant, known to all of you. So if I put these values in the equation, what shall I get? If I just calculate these things into calculators, I will get this value. It is 12.27 by root over of potential difference we are applying the electrons in Armstrongs. Clear? So this equation is very important. We will see very soon why. Because to prove this particle's wave nature, experimental physicists Davisson and Germer used a very important experiment. They tried to calculate the wavelength of electrons and tried to show their proofs with experiments. We all know that the objects like waves shows properties like interference and diffraction. Also reflection and refractions are also done, but we will work with these two nature. This experiment is called Davisson Germer. What did they try to aim? And their aim was, if they can prove that electrons, which are considered to be particles, have the properties to show diffraction, then we can conclude that these particles also have the wave nature. So we can conclude on de Broglie hypothesis. And they are very accurately proved it. Let's see how. This is the experimental setup of Davisson and Germer. This is a battery connected with a variable resistance so that we can change this potential difference V and this is the filament from where electrons are coming out, and these things are present. These are called collimators to keep the electrons beings come out as a straight. Here it is a C is the nickel crystal. On the nickel crystal surface, the electron beams hit, and from the small the atoms present in the lattice structure of the nickel crystals, the electron diffracts, and this is called Faraday's cylinder. This is actually a receiver which is connected to the galvanometer. The machine works that if the electrons coming out this filament hits here, and after that they spread in every directions, and this Faraday's collector can move in a circular path to find out in which angle the electrons are coming out, and the galvanometer connected actually shows the reading that the amount of electrons coming out of it. The galvanometer is a device which can show a very small amount of current flow. Now if the device is collecting electrons, then charges will be passing through it, and if charges are passing through it, then the galvanometer will give some readings which will show the electrons are coming out, and the amount value of readings will show from which direction we are getting the most number of electrons. So Davisson and Germer did what? They changed the value of potential difference and measured how much electrons are coming out at different angles for different values. They found out that mostly the graphs were proportional, means with angles they are getting nearly similar amount of electrons from each and every side. But the things started to change when they increased the potential difference up to 44 volt. They found out that the graph was no more linear, but there was a hump. Some bendings were occurring like this. That means at some angles which I will call phi, the electrons are coming out at highest amount. The electrons are coming out in highest amount. At 44 volt it started, and at the 54 volt this hump become maximum. At 54 volt the hump become maximum. It was like this. They found out that at 54 voltage potential difference and at the angle of 50 degrees, means this collection angle, this angle of collection of 50 degree, the things was the number of electrons coming out was maximum. Now see, there's a very strange thing occurring. You might be thinking what is strange, but if this is a bunch of particles coming out and diffracting from here, they should randomly go equal in each and every direction. So for every direction of phi, we should actually get a linear kind of graphs like this. But things like diffraction, it is quite similar to diffraction, is happening here. What is diffraction? And diffraction is the bending of waves at some specific angles, due to their passing through edges of sharp materials whose edges are equivalent to the order of their wavelength. In case of diffraction, we find out that at some certain angles, at some certain phases, the value of their waves are very high. Similar things are happening here, that at some certain angle the number of electrons coming out is maximum. So we had the formula that if the voltage is 54 volt, then the corresponding potential difference, the formula we calculated 12.27 by square root of V Armstrong. This formula we can put the value of B as 54, and the answer we get is that 12.27 by square root of 54 Armstrong, it is coming out 1.67 Armstrong. This was the estimated wavelength of electron. This was the estimated wavelength of electron using Davisson Germer experiment. Now it was further verified by Bragg's law of diffraction. Bragg's law of diffraction is mostly unknown to you, and it will take time to understand that. So for now, I'm just giving you the brief idea that if any kind of diffraction is occurring like this, see, this is the nickel surface from where the electrons are coming and then going out, and we found out that at the angle of 50 degree it is maximum at 54 volt potential difference. Now see, if I look at this thing and I make a perpendicular drawn on it, then this total angle is 180 degree. Out of this 180 degree portion, 50 degree is taken as phi. So what is remaining on these two sides? Now 180 minus 50, that is 130 degree. So each side is getting 65 degrees. 65 degrees. And this incident angle, this was called the incident angle, is also called the Bragg's angle. Bragg's law suggested that if theta is this incident angle of these things, then the corresponding wavelength of the object will be calculated like this. The incident related to the Bragg's planes is 2d sine theta. For nickel crystal, the value of V is 0.91 Armstrong. So if we put the values here, we can calculate that lambda equals to 0.91 into sine theta equals to 65 degrees. The value comes out in the order of 1.65 Armstrong. That means that electrons, their wavelengths calculated from Bragg's law was 1.65 Armstrong, and using the Davisson Germer experiment we have calculated the value to be 1.67 Armstrong. You can see these two are very same. They are nearly same. They are both 1.6 Armstrongs accurately. So you can say that yes, the electrons have the wavelengths which are verified from two different ways, and they comes out to be equal. So electrons, which was known till date as particles, as also showing a characteristics like diffraction. The Bragg's law of diffraction proves that electrons shows diffraction. That means particles have corresponding wave natures, and this was the very important discovery which was later verified by Davisson and Germer. I know I didn't mention about the Bragg's plane, Bragg's laws of diffraction. That's because this is beyond our syllabus. So we can go on this topic in further details later in our classes. But for now, this is it for the chapter. So thank you everyone, and if you have any kind of doubts, you can ask me in comments or you can also inbox me. Thank you.